What is measurement? Let's begin by thinking about how students develop specific ideas and measurement strategies. As a warm-up, take a few moments to consider these questions and do a quick scavenger hunt around your space. Don't worry about exact measurements or using measurement tools. Just do your best. Think about the measurement concepts you're using right now. Do you have a sense of what these different attributes mean and how you are visualizing the length, area, weight, and capacity of the differing amounts? Measurement is such an important and useful life skill, and there are plentiful real-world contexts and applications, such as driving distances, making recipes, and weighing produce. Yet it's a math topic that is not easy for students to fully understand. Suppose you presented this empty bucket to students and asked them to measure it. What are some of the questions you hope your students would ask? Think about this for a few seconds and then press pause and then hit play after you think about a few questions. As a teacher, you hope the students ask you, what about the bucket do we have to measure? Each aspect that can be measured is called an attribute. We can measure the surface area of the bucket, its weight, its capacity, or how tall the bucket is. Next, we have to choose a unit that has the same attribute being measured. For example, length is measured with units that are linear. Volume is measured with units that take up space, like cubes. When we use a tool to compare the number of units that are either filling, covering, or matching with the attribute of the object being measured, we describe this comparison of units by using a number. It is important for students to understand that the tool used must have the attribute of what is being measured. For example, we use a ruler, a linear tool, to measure the length of an object. The area of an object is measured in square units, the attribute of covering space. Measuring tools such as rulers and protractors make the measuring process easier and provide a standard form of measurement accepted by the math and science community. How do we provide students with rich and meaningful measurement experiences? This table outlines a sequence of learning experiences that students should progress through if we want them to have a deep understanding of measurement and using the right tools. First, students should compare objects using a measurable attribute. If exploring length, asking which object is longer or shorter keeps the focus on making observations about length, not learning how to use a ruler. Next, students use physical models of measuring units, such as using packing peanuts for finding volume or using index cards to measure the area of a desk. Again, students are experiencing what it means to find a measure of the attribute without adding the confusion of how to use a standard tool. Lastly, once students have the meaning of the attribute, we can introduce measuring tools. If a student has developed an idea about measuring using models, they will likely understand how a standard tool measures. We will explore this learning sequence in the next couple of slides. Imagine you are beginning to explore length with students. We can ask students which pencils are longer. Look at the paper clips underneath each pencil. What big ideas about linear measurement are we ensuring students attend to by lining up paper clips along a pencil? Take a few minutes to think about this question. This slide presents several key concepts about measurement in general. First, when we are covering, filling, or like in this example, matching units, we do not overlap units or have any gaps between the units. We call students' attention to the ideas of iterating a unit, that a composed unit is a measurement of single units. Zero is arbitrary. In this case, the pencil does not have to align with the end of the ruler to find its length. It is 4 paper clips long, as we see in the picture. And there is a relationship between units. A numeric measurement depends on the unit used. Using red paper clips produces a larger numeric measure, and using gray paper clips produces a smaller numeric measure. This relates to the idea of converting measurements, which can be challenging for some students to understand. Try to measure the length of your device or screen with your thumbnail. Your thumbnail is about 1 centimeter in length. How long is your device? As stated in the sequence of learning experiences, we start with using non-standard units. Unfortunately, many measuring activities do not begin with this essential step, which has many benefits for learners. It makes it easier to focus on the attribute, like in this case, length. We can use other non-standard units, such as paper clips and pieces of string. It avoids conflicting objectives in lessons. Imagine how many students associate measurement with using tools. What if our learning goal is to explore measuring length, not how to use a ruler? And exploring non-standard units provide a rationale for using standard units. What if in our world, scientists and mathematicians are working with and using different units? How would they communicate the correct quantities and measurements in any situation? When you feel students have an understanding of the attribute using non-standard units, we can move on to standard units. Having a measurement sense means that students are familiar with standard measurement units, can estimate using a particular unit, and meaningfully interpret measurement situations applying standard units. When asked questions such as these on the slide, the student will suggest reasonable responses. When developing student understanding of standard units, your learning goal should be around those ideas. Students should have an idea about the size of the unit and what it measures. They should be able to select a reasonable unit that comes with practice, and they should understand this relationship between units, which are larger and which are smaller. This helps with choosing a unit that will measure more precisely. And by progressing through the learning sequence mentioned earlier, students will develop these rich connections. Let's talk about the importance of estimation in measurement. When we estimate, we are using mental and visual information to measure something and make a reasonable guess without any tools. This process is connected to our spatial sense and ability to understand the magnitude of quantities. Think back to the warm-up activity at the opening of the module. Were you able to use your mental connections for length and weight and capacity? On this slide, you'll see a hyperlink to a website called Estimation 180. This is a site that provides several engaging estimation tasks using different attributes. For example, how many cheese balls will fit on the plate? What is a low estimate? What is a high estimate? Are you intrigued by the question? How close was your estimate with the cheese balls? Were you surprised? For students to improve their estimation, they have to practice, practice, practice. Here are some tips to help students learn how to improve estimation. The Goldilocks approach refers to a range of estimates. What is too high? What is too low? This helps students improve their accuracy as they discuss and compare their ideas and reasons why. Understanding the role of approximation is helpful in estimating. It is important to acknowledge that in all measurements there is some degree of error. Yet every time we use a smaller unit, we get closer to a more precise measurement. In our classrooms, we are responsible for providing experiences with both measurement systems, the US standard and the metric system. In my classroom, I used to spend a math lesson teaching students the history of the two measurement systems and how the metric system eventually became a global standard. We had great discussions, such as why did the rest of the world decide to use the metric system? Why do you think the US is resistant to changing systems? What areas of work do you think the US has to use in the metric system? To gain familiarity with both systems, I would have students do comparison activities with different attributes. Think to yourself, which is heavier, a kilogram or a pound? Which is a greater volume, a cubic inch or a cubic centimeter? If students are going to compete globally, we want them to understand and be comfortable with metric units. Now let's briefly talk about some of the key measurement attributes important to these grade levels. Length is usually the first attribute students learn to measure. The length of an object is found by locating two endpoints and examining how far or the distance is between the two endpoints. We begin to see many connections within the math landscape. The concepts of iterating and partitioning of a quantity are essential to the measurement domain. See in this example, we're iterating a unit of measure, 1 centimeter, 12 times to find the length of a pencil. And here we are partitioning 1 centimeter into 10 parts to find the length of an ant, or we can say we are iterating 1 millimeter 7 times. Experiences matter when it comes to converting measurements. And remember, we don't want students to rely on memorized conversion rules, but rather have conceptual ideas about the size of measurements and meaningful methods for conversions. By fourth grade, students are expected to be able to express measurements in a larger unit in terms of a smaller unit. Having students explore with the T-chart is one way for them to show the relationship between the different units, in this case, inches to feet. Students are also expected to be able to convert a smaller unit of measurement to a larger unit. Students who struggle with this conversion in the metric system are probably weak with base 10 and proportional reasoning ideas. This understanding is an example of how mathematics as a discipline is connected across the domains. Perimeter is the next attribute I want to discuss. Go ahead and pause here and take some time to solve this task using either grid paper or plain paper. Perimeter is the distance around a region or a shape, and because it is a length-based measure, it can be computed additively. What did you find as you explored the various shapes? This is a fixed perimeter problem. The perimeter does not change, but the lengths and widths of the rectangles do. What do you notice as you look at the rectangles? They move from long, skinny rectangles to rectangles that are more square-like as each side length becomes closer to the same value. As we think about this sequence of learning experiences, it's important that we begin to teach area by focusing only on the attribute. We want to develop the idea that area is measured by covering or tiling using models such as tiles, index cards, or even newspaper sheets. Remember, the definition of area is not length times width, as many students would say. It is the two-dimensional inside space of a region or shape. By fourth grade, students should be able to use their spatial reasoning to see the connection between using multiplication to find arrays and finding the area of rectangles. Area and perimeter are challenging concepts for students, perhaps because both involve shapes or because students are taught the formulas too soon for both concepts at about the same time. One suggestion is to give them activities such as this one so that you can contrast the two ideas at the same time. Here's a similar task as before. This time it involves finding different rectangles with a fixed area. Take a few minutes to solve this problem. Now we make pens that have a fixed area, but each pen has a different perimeter. Here are some possible questions you can ask students as they solve this problem. What is the area of a rectangle you just made? What is the perimeter? How is finding the area different from finding the perimeter? How do you measure area? How did you measure perimeter? This activity, as well as the previous pig pen with fixed perimeters, highlights a special relationship between area and perimeter. When the area is fixed, the shape with the shortest perimeter is most square-like. The skinnier the shape, the longer its perimeter, and the smaller its area. We noticed the same relationship in the previous slide. These relationships are constant in 3 dimensions. For example, in a 3-dimensional model, we can replace the perimeter with the 3D shape's surface area. And instead of finding the area, we find the 3D shape's volume.
All right, so here is your next part. Using just the 12 that you have for the area 12, create all the other ways you can find that area of 12, just using those. Now, you are more than welcome to reuse your tiles into whichever way you want. Draw out the outline of that shape. I want your math equation for area and the math equation for perimeter also. So find all the other ways you can show me the area of 12. Got it? All right, go for it. Keep going. Now find another way to find area using those 12. Use these blocks again. You can put them up there and arrange them how you want to create another shape with the area of 12.
Does it have to be in a rectangle?
You tell me. Every end needs to be touching. I need that. Please.
So we can do it your way now. It can be like fancy because we did it our way last time. Okay. We don't have to do it right there. How about we do it right here? Let's do it up like right here. I can't reach that though.
So you just go up.
Just look like it. Okay. So.
Remember when you're creating, be discussing with your partner, use your math words.
Well, let's do columns. Alright, and then these right here. And this one goes right here. And this one goes right. What? I don't get that. No. No.
It's not a rectangle.
She said it doesn't have to be a rectangle. As long as the sides are touching.
That's a square.
Alright, so let's copy it down. I'm gonna copy this side.
Can you do that side?
No, because you did it all.
Let me just do one side. I just want to do one side. Let me do one
It's over here. It's over here.
Oh my gosh, she was a rectangle.
It's 3 squares.
Only 3 squares.
I'll go 4 than 3.
How is that one different than that one?
Because it's turned.
What do you mean?
Like, instead of the 3 are on the top and bottom.
So what would we call those 3s? What would be the math? No, what would be that math word with the rays that we could call those 3s?
Columns. Columns or rows.
So the 3 would be what?
The columns.
So over here you're saying there's 3 columns. What about you saying over here?
There's 4 columns.
Okay. Now find a totally different rectangular shape you can create with the area of 12. Use these again. You can move them, manipulate them, however way you want to do them. But build me something else. Nope, only 12. Area 12. So you had to start all over. You cannot build this shape again. What other shape could you build to show?
Bottom and 6. Bottom and 6 on these sides, on the sides. You could do it like that. So 3 times 4.
Where is it?
So that was that one.
So you go over there and I'll let you know what's wrong, okay? Go, show us.
Want to make the rectangle at the outside of
Like that. So now yeah, but then now the sides aren't equal to the.
What is that?
So I'll put it next to it, I guess.
What is this number? That's a J. That's a J. Wait, didn't we just do that? Yeah, we just did. Yeah.
It's different now.
No, it isn't.
Yes, it is.
This
Technically,
is, you do it this way. Like we were.
it's different. Technically, all of them are the same.
Okay. Keep them. Like the stone.
P equals
Parameter equals 4.
no 16. Wait, 6 and 6 and 7 right there. Equals no 16. Yes.
I told you.
Wait.
What are you doing?
It's wrong. It's
6, 7, 8, 9.
that.
It's 8 plus 4 equals 12.
No. 12 plus 12. 24. Equals 12.
That is not 24.
24.
Oh, you just did it.
That means the P is wrong. Equals
How did you get 24?
Look,
Oh, because you had a
that's 12 plus 12.
12 plus 12
4
equals
and
20.
there's 4 and then there's 20. Okay, you gotta do a different one. We just tilt this one up, so it'll be easy if we go right here. We could go right here. 2. Wait.
2, 4, 6, 8, 10, 12.
Okay.
1, 2, 3, 4.
To where? 1, 2, 3, 4, 5, 6.
Then prove it. If you think you
We
can.
gotta see if it's that. That's not where we put the square U.
Maybe you gotta go to the other side.
Kind of floppy.
12 times 1.
The rough. Because the floor is rough. Because you fit.
I agree with you because that's just like this switched around. So I agree with you.
Okay, so what are you guys doing over here?
Explain
what you got so far.
So we did it like different ways and different ways.
What do you mean different ways? Give me some math words instead of different
It's
ways.
like we did different arrays. Like
How?
switching them. Like if this is like 2 columns and 6 rows, then this is 2 rows and 6 columns.
Oh, okay. Still finding the area and the perimeter though? Okay. Can you do me a favor? If you were saying that this one is 2, what did you say, 2 what?
2,
No, what did you call the 2? Did you say rows or columns?
2. It would be 2 on here. It would
Yeah.
be 2 columns.
So underneath the 2, could you write columns? And then underneath the 6, you would write,
Rows.
and then label that one over there. And then one of you could label these 2 in whichever way it is. Okay?
I'll do this side 1, 2, 3. The perimeter equals the perimeter is 16. 3 and 2 and 3 and 2. That would be a long one. And 3 and 2.
How is this different from this? It's different because this one has six rows and this one has 2 rows and this one has 2 columns and this one has 6 columns. But the area is still the same?
Yes.
Yours? Yours is that one.
Okay, and then 12. Here, don't do the same thing, almost the same thing as this. Do this one because I did the.
How do we introduce volume? By now you have the sequence of learning experiences down. First, the student has to focus on the attribute being measured by using physical models. For volume, we can pack various boxes of cubes or packing peanuts, which will result in good estimations and conversions. Again, students have to construct their own spatial ideas about what is being measured and how we're going to measure it. As a side note, capacity is another measure for the size of a three-dimensional figure. In terms of measurement, we talk about fluid capacity in terms of and use the units of quarts, gallons, liters, and milliliters. Here's a good example of incorporating a 3-act task into a lesson about finding volume. If you've never heard of 3-act tasks, I'm not going to get into them here, but I really encourage you, just do a Google search for Dan Meyer 3-act tasks. They're amazing. Notice the rich conversions between students as they grapple with finding the number of sugar cubes in the box. And I'm going to show you a video in a minute, but right now we're going to go through the 3-act process together. So, Act 1. What did you notice in that video? What did you wonder? How are the sugar cubes packed in the box? What are some of the dimensions you know are not accurate? Hit pause and take a minute and answer these questions before watching Act 2. Take a minute to see if you can figure out how many cubes. Hit pause and press play when you're ready. All right, how did you do? Now think about this task. Think about how we facilitated you trying to figure out how many cubes were in the box. Let's talk about the development of formulas. Why do we use formulas? Formulas are meaningful and efficient ways to measure different attributes of objects, and they become solidified when students have a conceptual understanding of the ideas and relationships involved. Students are less likely to forget what these formulas mean. They see that mathematics makes sense. First, we begin by using multiplication to determine how many squares will cover the area of a shape. Once students have this understanding, explain to them that we can think of one side of an area model as the base and the other side as height. Explain that either side can be the base. Then we begin to shift to using the formula area equals base times height. Students can then begin to see the relationship between the volume. Once we determine that a base of a box is 15 cubes, we can iterate that base 6 times, or we can decompose this prism using different layers. We can take the width layer and iterate it 5 times, seeing the associative property at work and being flexible with our groupings. Through exploration, we can establish that the length times width equals the base, and the base times the height gives us the volume. But here we can move to additive volume shapes. Understanding the derivation of these formulas, such as volume equals base times height times width, leads to more formalized thinking about the volume of complex figures in middle and high school, such as cylinders and prisms. Here's a slide showing how we can extend our thinking about volume with different tasks. Pause and try these tasks and see what you would do. What changes in the dimensions when the volume doubles? In 4th grade, students are beginning to learn about angles, another attribute that can be measured. Just as we did with the other attributes, we want students to focus on the meaning of what is being measured. We can use a non-standard tool such as an index card wedge and estimate how many wedges will fit into the angle. An angle can be defined as the arc of movement or spread between 2 rays joined at the same vertex. Some contexts that are used to describe angles are opening a door, moving a moving fan, or hands moving apart in a sweeping motion as angles rays. We measure one of the angles rays movement in degrees. And when one ray sweeps a full rotation, it moves 360 degrees, a full circle. Think for a moment which angle is bigger. This is a common misconception for students, that a wide angle with short rays is less than a narrow angle with long rays. Using tracing paper to overlay angles helps students see the spread is actually the same size. Moving students too soon to use a standard protractor may be one reason for the challenges with determining angle size. Here we see other tools to use besides protractors. We build a student's angle sense moving from using wax paper protractors or an angle estimator tool to using standard tools such as a protractor or angle rule. If they have a strong grasp of approximate sizes of angles, such as the difference between 90, 60, and 120-degree angles, then they will have the background knowledge needed to use standard measuring tools. As with other measurement attributes, angle measurement is additive, a part-whole idea showing how math is a coherent subject where concepts overlap among domains. Here is a which one doesn't belong activity using angles. This would be a great activity to informally assess students' use of vocabulary such as vertex, rays, line segments, and more. Remember the goal of a which one doesn't belong, a WODB, is to have students discuss and justify their noticings. All answers are possible. For example, A is the only one that doesn't show arrows, and D is the only angle that looks smaller than the others and doesn't look like a square corner. The rays aren't as far apart. This is a fun, engaging activity that is accessible to all students. By the way, if you want to access more of these, there is a website called WODB, which one doesn't belong.com. Here's a recap of our learning targets. Press pause and read through these and think about if you feel like you've met these targets.